Hi, this video is the second part to my bond structure properties and energy changes chemistry 2.4 revision video, and we're going to be looking at the crystalline solids, the four types of crystalline solids, and the types of structure and bonding in them, and the properties that you need to explain about them. Okay, so let's get on with the video. First up at crystalline solid, we're going to look at molecular solids. So an example in the picture of a molecular solid we can see here is iodine, and here we can see that the iodine is subliming. You may have seen this in your chemistry class. You put some iodine crystals over a moderate heat, and the solid will just change straight to a gas. Now the reason that the solid does that is that the bonds, which are called weak intermolecular attractions, between the I2 or the iodine molecules, the two iodine atoms bonded together and appear, are weak, and it takes very little energy to break them, so they break apart and they become a gas. Now this is kind of distinctive about molecular solids. Molecular solids are made up of what we call discrete molecules that are held together by weak intermolecular attractions. Now, because they're made up of these discrete molecules, they have the following properties. So they have a low melting point. Now that is because these solids have discrete molecules bonded together by these weak attractions. It only requires a small amount of energy to break the weak attractions between the particles. And when we break those attractions, we then can change a solid into a liquid. And if we break all of the attractions, we can change a liquid into a gas. So that's why they have low melting points, because it takes very little energy to break the weak attractions between the discrete molecules. They are soft for the same reason, but when we explain about them being soft, we don't say that there is only a little amount of energy needed. We say there's only a small force needed to break them. So if I want to fracture or break these things, only a small force is needed to break the weak intermolecular attractions that are holding these discrete molecules together, or the particles and the solid together. These are the two most important properties. There is one also about solubility. And the thing about these is they don't dissolve in water, which is a polar liquid. Now, polar liquid is a liquid that is made up of particles, or molecules that are actually polar, like water. We'll look at that a bit later. So they won't dissolve in polar liquids because they can't form attractions with the polar liquids that are stronger than the attractions of polar liquids have for each other. So let's have a look at this really. So if I took some hexane, and hexane is an example of a discrete molecular solid that's held, the discrete molecules of hexane are held together by weak intermolecular attractions. So this is an example of molecular solid. Now, if I want to put the iodine and try and dissolve it in the hexane, now remember the iodine had exactly the same type of attractions, these weak intermolecular attractions. Well, it's very easy to break these attractions and have these two different types of molecules that have weak attractions to form weak attractions of similar strength between themselves. So this will end up having the iodine molecules dissolved in the hexane. Now, so these are both called non-polar. So this is a non-polar solvent. So molecular solids usually dissolve in non-polar solvents, because non-polar solvents generally are a good example of molecular solids that are liquids. So the reason this happens is the molecular solid of iodine, it can form weak attractions with the hexane that are just as strong as the attractions that the iodine molecules had to each other, or the hexane molecules have each other. So they just break apart and reform, and they dissolve. Okay, if you want to just look at exactly how you might write an explanation of this, you can stop the video and look at my explanation below in detail. Okay, so this slide here should say molecular solids are insoluble in polar solvents or insoluble in water. So here's a wee diagram of water. We can see that the water molecules are arranged in a specific orientation. Now, they're not all like this in liquid water, but parts of liquid water are arranged like this. They do have these reasonably strong intermolecular attractions between the water molecules. Now, remember, our iodine molecules had quite weak intermolecular attractions. Now, the problem that we have here is because the water molecules have quite strong intermolecular attractions, and it's because they're polar, so their negative and their positive ends can have attractions to each other that are significantly stronger than these just weak attractions between these non-polar iodine molecules. There's no way that these iodine molecules are going to make attractions as strong as the water molecules have for each other, so they can't actually break into the middle of these water, into the middle of the water here and make new attractions. Or we say that the attractions between the molecules and the water molecule is not as strong as the water-water attractions. That's why they don't dissolve. So these are either just going to sit on the bottom of a solution of water, or if it's something like cyclohexane or hexane, it's just going to float on the top of the solution. They will not dissolve. They're not miscible. Sorry. An interesting property of water is that it is polar, which means that it has these positive and negative sides to the water molecules. The sides with the two hydrogen atoms on are slightly positive because they're less electronegative, and the side with the oxygen is slightly negative because it's more electronegative. Remember, we talked about with polar molecules that the bond between the hydrogen and the oxygen has that the atoms have a difference in electronegativity, so they share the electrons unequally. The oxygen gets a bigger share of the electrons, becomes slightly negative, and the hydrogens become slightly positive. And overall, because this is an asymmetric shape, it produces a polar molecule. Now, if we're dropping a stream of a polar molecule, like if you have turned a tap on and you've got a stream of water falling straight down, it's actually interesting that this stream will veer towards a negatively charged balloon, a balloon that you've rubbed against a jersey, a jumper, or your hair, will become negatively charged. And what actually happens is the water molecules in the stream will reorientate. They will twist until the positive side of the water molecules will face the negatively charged balloon. And then, since the positive side is facing the negatively charged balloon, they're going to be attracted, and this stream of water is going to bend, and we're going to notice a bend. And this is a peculiar property of water. It's attracted to, excuse me, to charged objects. So we have what's called an electrostatic attraction. So this is a really good way to determine if a stream, a liquid is a polar. We can put the liquid in a burette. We can let the water slowly out the bottom of a burette and put a negatively charged balloon next to it, or maybe a rod or a ruler. And if the liquid is the path of the water, sorry, the liquid is bent towards the charged object, then it is a polar solid, or actually in this case a polar liquid. So the next type of solid we're going to look at is covalent network solids. Now they are regular 3D networks of atoms held together by covalent bonds. They're actually one giant molecule that you can see with your eyes. And there are only three types that we need to know about. That is diamond, graphite or graphene, and silicon dioxide or quartz. So let's have a look at the first one here is diamond. So here's a picture of an uncut diamond here. Here's a diagram of how carbon atoms are bonded to. So you can notice if we find a carbon atom in the middle, it's bonded to 4 other carbon atoms in the molecule. Now this regular 3D arrangement will go on for millions of atoms deep, millions of atoms high, millions of atoms wide. And when it gets large enough, we can see it as a solid object. Now, every single bond between the atoms, between the carbon and the 4 other atoms it's bonded to, is a covalent bond. Hence, it's called a covalent network. We can see the network solid. These covalent bonds are very strong. Okay, so they're strong, and it gives these solids their distinguishing properties, which is they are very strong and they have very high melting points. They're made up, so if we wanted to write this, explain this in a nice structured paragraph, we would say that these covalent network solids are made up of atoms bonded together by very strong covalent bonds. These atoms are arranged in a regular 3D lattice where each atom is bonded to 4 other atoms, and we can see this is a tetrahedral arrangement. Now, because these covalent solids have very strong covalent bonds, it takes a large amount of energy to break these bonds that hold them together in order to melt them and make them become a liquid. So in order to turn a solid to a liquid, we have to break a significant amount of these bonds. So we need a large amount of energy to break them, and that's because they have very strong covalent bonds. Also, they are very hard. And remember, when we're talking about hardness, we're saying that it needs a lot of force to break the strong bonds. Now, really hard means if I'm going to rub diamond against something, it's going to scratch the things that we rub it against, which is why we can use diamond to etch glass. It will etch just about anything. They do not conduct electricity. Now, the reason it will not conduct electricity is because the atoms in the 3D network, or the regular 3D lattice, are held together held by 4 bonds to the other atoms around it. And the atoms aren't free to move. And as well as that, the atoms have no charge, so it can't conduct electricity. Now, actually, graphite is an exception of a specific type of covalent network where we can conduct electricity, and we'll look at that in a couple of slides. So solubility, this is going to be quite straightforward because the bonds are so strong. Whatever liquid that we place the solid in, they're not going to be able to form bonds with the liquid particles that are stronger than the bonds they have within themselves. So they will not dissolve. So the bonds between the atoms and the covalent network are so strong that they're not going to stop these bonds and form new ones. So therefore, they're insoluble in water, and they're insoluble in non-polar solvents as well. So another example of a covalent network is silicon dioxide. And you can see from this diagram here, the silicon represented by the black spheres, the oxygens by the blue spheres. We have covalent bonds between the silicon atoms and the oxygen ones, and it produces a very strong tetrahedral structure. It's arranged a wee bit different than a than a diamond. It's not quite as strong as diamond, but it's still a regular 3D lattice with very strong covalent bonds, so it's going to have the same type of properties. Here is a picture of a piece of graphite. Now, graphite is an exception to the other covalent network solids. The reason it's an exception is because graphite is actually a 2D structure. So it's like a sheet of paper. It's flat. It has a plane. So it has width and it has height, and depth, but it's got no height. Just one atom thick, right? So what happens in graphite is actually each carbon atom is bonded to 3 other carbon atoms. Now this leads to a really interesting property of of graphite. Because each carbon atom usually has 4 electrons in its outside valence shell, and it's only using 3 of these electrons to form bonds, it has 1 electron spare. So every one of these carbon atoms has a spare electron, and that spare electron will end up becoming delocalized, or it can move around this 2D lattice. So we can say that graphite is a 2D covalent network substance. It consists of layers of carbon atoms bonded in hexagon rings by strong covalent bonds. Each carbon is bonded to 3 other atoms, and there are delocalized electrons as well. I didn't write it in this blue. So let's have a look at it in a different way. So here is my, I've just skewed this two-dimensional lattice of graphite here, and I've shown here in blue the delocalized electrons that are with each atom. Now what actually happens here is if I apply a positive charge to one side and a negative to the other, so essentially what I'm going to do is provide a electrical current, then the electrons will move towards the positive charge. This flow of electrons is a flow of an electric current. So these two-dimensional graphite structures will conduct conduct electricity because they have free moving particles that have a charge, and these free moving particles are the delocalized electrons. So the reason they conduct is that there are particles that are free to move and have a charge, and those are the delocalized electrons. Final interesting property about graphite is we said that they are two-dimensional covalent networks, but each of these two-dimensional layers is actually laid upon another two-dimensional layer, and in between the layers we have weak intermolecular attractions. Okay, so within the layer, between each atom, are strong covalent bonds, but between the two-dimensional layers are weak intermolecular attractions. Now that gives graphite its a special properties that means that when we put graphite onto solid objects, often they slide. If you put graphite onto a surface and you put your hand on it, it will become very slippery. And it's because you have multiple two-dimensional layers sitting on top of each other, and they just slide past each other because these bonds between the layers, these weak intermolecular bonds, can be easily broken. Okay, and that's remember the reason that the two scientists, I forget their names, who won the Nobel Prize, were able to separate graphene layers, each individual layer, from each other, is because the attractions between the layers were so weak. So now let's look at metallic solids. So they have their own specific group of properties based on their particles and the bonds that make them up. Right, metallic solids. So anything that you would sort of notice and call a metal is basically a metallic solids, and they have the same type of arrangement. They're also a regular 3D lattice. They're made up of atoms and delocalized electrons. So if this was steel, which is mostly made up of iron, we would have iron atoms with delocalized electrons around the outside. They're held together by what we call strong covalent bonds. Sorry, not covalent bonds, strong non-directional metallic bonds. Now, what we mean by non-directional, if you can look at this delocalized electron I'm just pointing to here, it has this electrostatic attraction to the nuclei of each of the atoms around it. These attractions are not in given directions, so as the electron moves, the actual direction of the attraction will change, so they're called non-directional metallic bonds. And they're strong because they're negative and positive attractions, or electrostatic attractions. So we would say metallic solids are made up of atoms arranged in a 3D lattice held together by strong non-directional metallic bonds between the atom nuclei, or the nucleus of atoms, and the delocalized electrons. Now, because metallic solids have these strong attractions, they have high melting points. It takes a lot of energy to break the strong metallic bonds holding these particles together, holding the atoms and the delocalized electrons. Now, if I wanted to write an explanation as to why they have high melting points, I would have to write the part in blue first, that is describing the type of particles and how they are arranged, and the bonds that are holding them together. They're strong non-directional metallic bonds. And then I'm going to go on and explain why they have high melting points. Same reason that they have high melting points for the other solids or low melting points. It's to do with the amount of energy that's needed to break the bonds. These are strong bonds. They need a large amount of energy, so they have high melting points. And then we would expect they're also hard, okay, because they have strong bonds, strong metallic bonds. They're going to need a large force to break them, so they are hard. Now, there's another couple of interesting properties about metallic solids. Often you're asked about these in assessments. The first one here is malleability. So if we take a metallic solid and we hit the metallic solid with a mallet or a hammer, what's going to happen is they're going to deform, but they're not going to fracture. So they're going to bend. The atoms are going to keep their attractions to the delocalized electrons. They've just moved as the forces push them. Now, the way that we'd explain this is the metallic solid is made up in this 3D lattice held together by non-directional metallic bonds. So what's important is they're non-directional. Now, as between the nuclei and the delocalized electrons. Now, because these bonds are non-directional, as the particles move past each other, as they're pushed past each other, the bonds will actually diminish and then reform without breaking. Okay, so they can move past each other, they can get less and then increase again, but without breaking as the delocalized electrons in the atoms move. So the last property we're going to have to talk about with metallic solids is they're able to conduct electricity. And the reason they can conduct electricity is because they have these delocalized electrons. And remember, an electron is, in this case, is free moving because it's delocalized and it has a charge. So what's going to happen is when we apply a positive and a negative end circuit to this, we're going to get the electrons moving towards the positive side because they're negative, and we'll get electric current flowing. So if we were to explain this in a paragraph, we would say, okay, we've got a metallic solid. It's made up of atoms held in a regular 3D lattice, held together by non-directional metallic bonds between the nuclei. Okay, the attraction is between the nucleus, remember, and the delocalized electrons. Because these delocalized electrons have a charge and are free to move, it will conduct electricity. Okay. So the last type of solid we're going to look at are ionic solids, and ionic solids have their own distinct properties and structure. So we often recognize ionic solids in the wider world. When they're solids, they'll look like crystals. Now, sometimes they're small crystals and sometimes they're larger crystals. Now, they're crystals because the ions that make up the solid are arranged in a regular 3D lattice, and an interchanging or an alternating arrangement between positive and negative ions. So that the positive ions are next to the negative ones, and the negative ones are next to the positive. Now that leads to a very strong attraction because the ions are very close to each other and they're oppositely charged. This is electrostatic attraction, but we usually just call them strong ionic bonds. So these strong ionic bonds, remember, are between the positive and the negatively charged ions. So we can say ionic solids are made up of alternating positive and negative ions held together by strong ionic bonds in a regular 3D. Okay, so ionic solids, we've talked about the alternating positive and negative ions held together by strong ionic bonds in a regular 3D lattice. Because they have strong ionic bonds, they have high melting points because it takes a lot of energy to break those bonds. Because the particles are ions and ions are charged particles, negatively or positively charged, they can actually move to a positive or a negative side when an electrical current is put to them. So they can move to a positive end or a negative end. So they can conduct electricity, but only when they're liquid. Now, a ionic solid is liquid. It's called molten. It's been heated enough to turn it to a liquid. Then the positive and negative ions are free to move, and they can transmit charge because they're charged and they're free to move. Actually, if they're dissolved in water, the particles are also free to move, and they'll conduct electricity then. So there's 2 times that ionic solids can conduct electricity. However, when they're held together by strong ionic bonds in the regular solid lattice, they cannot conduct, even though they have charges, a positive and negative charge. They can't conduct because they're not free to move. Right. Why do ionic solids dissolve in water? So, the reason that ionic solids can dissolve in water is because water are polar molecules. They have this negative end and this positive end. The positive end, remember, is the side with the wee hydrogen atoms on them. In this case, the hydrogen are the red atoms. On the side of the water molecule here with the red atoms, it's slightly positive, and on the side that's more got the white atom sticking out is the oxygen side here. We have this negative side. So the positive side, what happens is they line up next to the negative ions, and they form such a strong attraction, or where there's enough of them to form a strong enough attraction that they will actually pull this negative ion away from its lattice and then surround it and have it dissolved or surrounded by water molecules. And by having the water molecules change their orientation to on the positive ions, they'll do exactly the same thing in the opposite way. So in that case, water molecules can dissolve ionic solids by slowly just pulling away each ion from the attraction that the poles of the water molecules have for the negative and positive ions. Now, obviously, the attractions between the water molecules and the ions are just as strong as the attractions that the ions have for themselves within the lattice, and that's why they can dissolve. Okay, so the last property we want to look at to do with ionic solids is them being brittle. Now, if we hit an ionic solid with a force, in this case I've got a hammer, this is kind of a miniature hammer if this is the actual micro, because imagine the ions are very small, but let's just ignore that. So if I hit this regular lattice with a hammer and I shift a couple of columns of these down a wee bit, notice that as they shift down, the positive ions move into alignment with the positive ions and the negative ones with the negative ones. We now have an electrostatic force happening that is pushing them apart instead of attracting them together. So we've got a force pushing them apart, and that produces what's called a fracture. It produces a fracture, and the crystal that is this ionic solid will break, and we can't put it back together again. It's not easy to put it back together again, but it'll break in these nice clean lines, or we'll get these sharp breaks, and it's distinctive of ionic solids, and it's because we get this arrangement where the ions become adjacent to ions of a similar charge. So we can say ionic solids are made up of alternating positive and negative ions bonded together in a 3D lattice. Ionic molecules are not malleable because if pressure is applied to an ionic lattice, it forces ions with the same charge next to each other. They repel and break the structure. And those are all the properties that we need to know about for the 4 different types of solids that we can organize matter into. If you spend the time and go over those, you should be reasonably confident that you can answer any questions they might give you in an exam on this type of scenario. I hope that's been useful. If you like the video, don't forget to like it and recommend it to others. Thanks a lot.